All right, let's go. Number 8, Cherenkov Radiation. There's a rule everyone knows. Nothing travels faster than light. It's basically the first law of the universe. Except it has a loophole, and the loophole glows blue. Here's what they don't always tell you. The speed of light, 300 million meters per second. That's its speed in a vacuum. Put light inside water, inside glass, inside dense material. It slows down, sometimes dramatically. And that's when things get interesting, because other particles, they don't slow down the same way. A high-energy electron fired into a nuclear reactor's cooling water can actually outrun the light moving through that same water. Not faster than the universal limit, faster than light in that medium. And the universe notices. When a charged particle breaks that local speed barrier, it creates a shockwave. Not a sound wave, a light wave. The same way a jet breaking the sound barrier creates a sonic boom, this particle creates an optical boom. And it glows. That blue. That eerie, unmistakable blue you see in the core of nuclear reactors. That's not a malfunction. That's the signature of something moving faster than light can move in that environment. Cherenkov radiation is real. It's measured. It's used in particle detectors worldwide, and it tells you something quietly uncomfortable. The speed limit isn't always the same number. It depends on where you are and what's around you. If the speed of light can change, what else about physics is more flexible than we assumed? Number 7, Superluminal Motion. Astronomers pointed a telescope at a jet of plasma shooting out of a distant galaxy. They measured its speed. Then they checked their math. Then they checked it again. The jet appeared to be moving at 7 times the speed of light, across the sky in plain sight. No exotic physics, no wormholes, no theoretical hand-waving, just a jet moving impossibly fast. Except here's the thing, it wasn't. What they were seeing was geometry playing a trick at relativistic speeds. When a jet of material fires toward you at close to the speed of light, nearly parallel to your line of sight, something strange happens to the timing. The jet is chasing its own light. Each pulse of emission arrives almost at the same time as the one before it, compressed, stacked. And when you plot the apparent position over time, the motion looks faster than it actually is. Much faster. Sometimes 5, 6, 7 times the speed of light. It's called superluminal motion, and it's not an illusion in the dismissive sense. The math is real. The measurement is real. The effect is real. What's happening is that space and time are conspiring to make relativistic motion look even more extreme than it is. Think about that. The universe is already doing something wild enough to require special relativity. And then the optics of special relativity make it look even wilder. We've now detected superluminal motion in dozens of jets across the observable universe. Quasars, active galactic nuclei, gamma-ray burst afterglows. It's not rare, it's practically a feature. And if geometry alone can fake faster-than-light motion, what happens when the physics itself starts bending? Number 6, quantum entanglement. Two particles, created together, then separated. You take one to the other side of the planet, maybe the other side of the galaxy, doesn't matter. You measure one, and the other one instantly reflects that measurement. Not after a signal travels between them, not with a slight delay, instantly. Faster than light could have carried any message. Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete, that there had to be hidden variables, some underlying mechanism, some information traveling between them that we just couldn't see yet. He was wrong. In 1964, physicist John Bell designed a test, a way to mathematically prove whether hidden variables existed or whether the universe was genuinely, irreducibly strange. Experiments ran. Results came in. Hidden variables lost. The universe is genuinely strange. When you measure one entangled particle, The other one doesn't receive a signal. There's no signal. The correlation just exists across any distance, at no speed, or infinite speed, depending on how you frame it. Now, physicists will tell you, correctly, that you can't use entanglement to send information. The correlation is real, but you can't control what result you get. So no faster-than-light communication, no violation of causality, technically. But here's what keeps physicists up at night. Something is connecting those particles, something that doesn't care about distance, something that operates completely outside the speed of light framework the rest of physics runs on. We don't know what that something is, we just know it works, every time. And if the universe has connections that operate beyond the speed of light, how deep does that go? Number 5. Tachyons. What if there was a particle that couldn't slow down? Not won't, can't. A particle so fundamentally different that the speed of light isn't its limit. It's its floor. Meet the tachyon, the hypothetical particle that has never been detected, never been confirmed, and yet refuses to leave physics. Here's why it keeps showing up. Einstein's equations describe how mass increases as you approach the speed of light. At light speed itself, infinite mass, infinite energy required. That's why you can't get there. But the math doesn't actually forbid what's on the other side. If you start with imaginary mass, mathematically imaginary in the formal sense, the equations still work. And what you get is a particle that always travels faster than light. Always. Slow it down and it gains energy. Speed it up and it loses energy. It's the mirror image of everything we know, the bizarre twin of normal matter, living permanently on the other side of the light barrier. Now, we haven't found one, but here's where it gets uncomfortable. Tachyon fields appear naturally in quantum field theory. String theory uses them. The Higgs mechanism, the physics behind why particles have mass, is mathematically related to tachyonic condensation. The tachyon isn't just science fiction. It's a mathematical structure that keeps emerging from the equations whether we invite it or not. And some physicists think that means something, that the universe might have a faster-than-light sector we simply haven't learned to look into yet. Or maybe the math is telling us something stranger, that speed itself is more complicated than a single number. Number 4. The Alcubierre Drive. In 1994, a physicist named Miguel Alcubierre did something audacious. He sat down with Einstein's field equations, the same equations that say you can't travel faster than light, and found a solution that gets you across the galaxy in any amount of time you choose, legally. No laws of physics broken, no particles exceeding the speed limit. Here's the trick. You don't move through space, you move space. The Alcubierre metric describes a bubble of flat space-time surrounded by a wave. Space contracts in front of you. Space expands behind you. You sit inside the bubble, technically stationary, while the bubble itself surfs a distortion of space-time faster than light. The speed limit applies to objects moving through space. It says nothing about space itself moving. And we know space moves. We've measured it. That's what the expansion of the universe is. Space stretching. Galaxies carried along. No speed limit applies. So Alcubierre asked, what if we did that on purpose? What if we engineered a region of space-time that contracts and expands around a ship? The math works. Einstein's equations allow it. The problem, and it's a significant problem, is the energy required. Early estimates suggested you'd need the mass energy equivalent of an entire planet. Later refinements brought that down. But the drive still requires something called exotic matter, negative energy density, material that, as far as we know, doesn't exist in usable quantities. Except, the Casimir effect suggests negative energy is real, small, fleeting, but real. So the Alcubierre drive isn't fantasy. It's an engineering problem we don't yet know how to solve. And there's a difference between those two things, a significant one. But even if we could build it, the universe has already been running its own version of this drive since the very beginning. Step 7, number 3, cosmic inflation. Number 3, Cosmic inflation. In the beginning, the universe was smaller than an atom. Then, something happened. Something violent. Something that makes every explosion in the history of the cosmos look like a candle flickering. In a fraction of a second, a fraction so small it doesn't have a name you'd recognize, the universe expanded by a factor of at least 10 to the power of 26. That's not a typo. That's the observable universe going from subatomic to the size of a grapefruit, instantly. And the speed of that expansion? Incomprehensibly faster than light. Not a little faster, not twice as fast, billions of times faster. Now here's what makes this different from everything else on this list. We have evidence. The cosmic microwave background, the oldest light in the universe, is almost perfectly uniform in every direction we look. Too uniform. If the early universe expanded slowly, different regions would never have had time to reach the same temperature. They're too far apart. But they did reach the same temperature, somehow. Inflation explains it. Before that expansion, everything was close enough to equilibrate. Then inflation stretched that uniformity across the entire observable universe. We also see it in the large-scale structure of galaxies. The tiny quantum fluctuations from before inflation got stretched to cosmic scales and became the seeds of every galaxy, every cluster, every filament of structure we observe today. Inflation isn't fringe. It's in the textbooks. It's in the data. The universe broke the speed of light before physics even had time to stop it. And here's the part that doesn't get easier the longer you sit with it. If inflation happened once, there's nothing stopping it from happening again, somewhere else, right now. Number 2, Hubble flow. Pick any direction at all. Look far enough, and you will find galaxies moving away from us faster than light. Not some galaxies, not distant anomalies, all of them. Past a certain distance, roughly 14 billion light years, every single galaxy is receding faster than light, right now. While you're watching this. This isn't theoretical. This is the measured, confirmed, Nobel Prize-winning structure of the universe we live in. It's called the Hubble flow, and it works exactly like the Alcubierre Drive did on paper. Space itself is expanding. The galaxies aren't moving through space faster than light. The space between us and them is simply growing faster than light can cross it, which means those galaxies are now permanently beyond our reach. Not temporarily, not until we build better ships, forever. No matter what we do, no matter how long we wait, they are gone. The light they emit right now will never reach us. It's moving toward us, but the space between us is expanding faster than that light can travel. Let that land. There are galaxies, real existing galaxies, full of stars, planets, possibly civilizations that we will never see. Not because they're hidden, because the universe is pulling them away faster than information can travel. We are already, right now, cosmologically isolated from most of the universe, and it's getting worse. Every second, more galaxies cross that threshold. Every second, our observable universe gets a little more lonely. But here's what that implies. If space can expand faster than light, if the vacuum of space itself has this property, then maybe the vacuum isn't as empty as we've been assuming. Number 1, the quantum vacuum. Empty space isn't empty. It never was. At the smallest scales, below atoms, below quarks, below anything we can directly measure, space is boiling. Particles flickering in and out of existence. Energy appearing and vanishing in intervals so brief they technically don't violate the laws of physics. This isn't metaphor. This is measured. The Casimir effect proves it. Place 2 metal plates close enough together in a vacuum. They attract, not because of charge, not because of gravity, because the vacuum between them has less energy than the vacuum outside them. The nothing is pushing them together. The nothing has structure. And here's where this connects to everything you just watched. Cosmic inflation, driven by vacuum energy. The Alcubierre Drive requires manipulating vacuum energy. The expansion of the universe, accelerating right now, pulling galaxies past the speed of light, powered by vacuum energy. The quantum vacuum isn't a backdrop, it's the engine. It's the medium everything moves through, and we have almost no idea what it actually is. Our best calculation of how much energy the vacuum should contain is off from what we measure by a factor of 10 to the power of 120. That's not a rounding error. That's the largest discrepancy between theory and observation in the history of science, which means one of two things. Either our physics is missing something enormous, or the vacuum itself is doing something we fundamentally don't understand. And here's what makes this the deepest entry on this list. Every other object we covered moves faster than light through space, or bends space, or appears to cheat the limit. The quantum vacuum doesn't move through space. It is space. It's the thing doing the expanding. It's the thing inflation acted on. It's the thing entanglement may be threading through. It's the floor of reality, and it's already moving faster than light in every direction simultaneously. You're not sitting in empty space. You're sitting in something we can barely describe, something that expands, fluctuates, flickers, and has been doing all of this since before the first particle existed. We didn't find 8 things faster than light. We found 8 windows into the same unsettling truth. The universe doesn't run on the rules. The rules run on the universe. We like to think the speed of light is a wall, a hard boundary, the universe's final rule. But what we've seen tonight suggests something quieter and stranger. The limit was never about speed. It was about information, about causality, about what can affect what. And the universe, in its inflation, its vacuum, its entanglement, has been operating beyond that boundary since before the first second existed. We're not breaking physics. We're just finally starting to read it. Stay curious.